Greetings, everybody. It's 1 o'clock here in the Mountain States, and it's time for Lecture 5 of our Cosmology course. Lecture 5 is broken into several separate files. So if you look in the file or the notes archive where I've been storing the notes, you're going to find five files in there, different topics related to what are our cosmological signals that we go looking for and what are the observatories that we use to look at those potential signals. If I didn't break it into parts, the file would be just too big to manage. So let's get going. Here's an interesting occultation. This is called an occultation when a planet crosses the face of the sun. And this is, I don't know when this was done. It happens every, I don't know, 10 or 12 years. Mercury or Venus cross the face of the sun. And there's Mercury. So this is the first part. How do we observe the universe? We apply a lot of different technologies. Historically, of course, telescopes were the first. Well, the human eye was first, but then telescopes enhanced what humans could see without the aid of telescopes. And we're going to go through that history and make sure you understand the evolution of different strategies for viewing the cosmos. But before we do that, let's talk a little bit about what it is we look at. Well, I mean, pictures are nice. And as you know from looking at pictures from the Hubble Space Telescope and James Webb Telescope and so forth, the pictures can be just really dramatic, particularly when we consider that each of those pictures contains, in many cases, thousands or millions of galaxies in which there are trillions of stars in every galaxy, and for the part of the universe we can observe, namely the Milky Way, when we look for planets, we find the probability that a star will have at least one planet is approximately 1. There almost certainly a planet orbiting every star. Then there are obviously exceptions. There are also stars that have many, many planets orbiting them and so forth. So when we look at these pictures, they can be really emotional when you consider the possibility that there's life near those millions of stars we see. But we also want to do science. And the way we do science is look at spectra. Here's an example of spectra from JWST, finding atomic elements just like the ones that are here on planet Earth. And these are in the visible wavelengths from about right here outward. Humans cannot see this. This is ultraviolet spectrum, or ultraviolet. We also can't see the spectra that are produced when we look at the universe with X-ray telescopes. And here are some examples of different elements that we see using looking at X-rays emitted by galaxies and so forth. So when we talk about cosmological signals, we're looking for any source of astronomical, astrophysical, or cosmological significance. And in the first lecture, I tried to make a distinction between these three things. Some people say astrophysics, which is understanding how stars and galaxies produce the signals that we ultimately detect. That process of production of those signals goes under the topic of astrophysical, because in many cases, we have an understanding of what's going on in the stars. Astronomy, for a lot of people, including me, is sort of a observational property or observational capability that humans have had since even before there were telescopes. And cosmology we're looking at light sources associated with the Big Bang and particle physics and things that we don't understand. So usually, and for most of history, the signals that we have detected have come from electromagnetic radiation, that is, different versions of light, like I'm illustrating here. Ultraviolet light that we can't see, visible light we can see, X-rays we can't see, radio signals, and so forth. But lately, say in the last 20 years or so, we've expanded our scope, and we now are detecting particles, that is, particles generated in various astrophysical phenomena, and really studying those in detail. And gravitational waves we're going to talk about during this presentation today. This is a whole new window since about 2017 on the universe, and a very powerful window indeed. And other things we will get into, as I've said and illustrate here, spectroscopy is critical to our understanding. It gives us information about the expansion rate of the universe, the composition of stars, the composition of galaxies, and a variety of other things. And we're also interested in the gas and dust that is the bulk of the universe. You might remember from last time we were looking at the pie chart of the different types of energy that exist in the universe. And among all the forms of energy, only about 5% is atomic in nature. The rest is dark energy or dark matter. And among that tiny fraction that's atomic, most of it is just gas floating between the galaxies, not in stars, not bound up in planets or anything like that. So this interstellar gas and dust being physical chunks of maybe molecules and so forth. That's the bulk of the universe in the part of the universe that is atomic. So we're looking at that. And to make sure that we're understanding what we're looking at, we have to go in the laboratory and look at the spectra that we can for the various species of atoms and molecules that we observe out in the stars. We want to go in the lab and make sure we're accurately identifying what we're looking at. We use particle accelerators. I've mentioned a number of times the facility in Geneva where they crash protons together to see what are the component constituents of the things we see out there in the universe. Nuclear reactors are a source of course, radiation, but also strange particles called neutrinos. So we're doing things here on Earth and looking at the stars and galaxies all at the same time to assemble a library of cosmological signals. And here's what we get from doing that. And we've covered all this in prior lectures, but it's useful to recapitulate what we've been doing. From the information we're getting from the cosmos, we can get details of the early universe, the cosmic microwave background, the baryogenesis, that is the creation of atomic matter in the early universe. We measure the expansion rate of the universe, the current expansion rate, and we can infer the expansion rate that existed earlier by looking at the light we get from the cosmos. We look at the different composition of stars, that the gas clouds between the galaxies, the composition of galaxies, and we now describe, but do not yet understand, the dark part of the universe, that is dark energy and dark matter. Those topics remain mysterious. We understand the mass density of the universe. If you take a cubic meter of empty space, we have a self-consistent understanding using different scientific methods for knowing what's in that that sample, if we could make that sample, and that tells us the expansion rate of the universe and the energy densities. We measure the age of the universe. Here's the energy density I just mentioned. And from the energy density, we get the geometry of the universe, but not the shape. And we've been through that discussion before. And all of this put together gives us the ability to do a prediction of how the universe is going to continue to evolve, whether it's going to continue with the accelerating expansion that has been observed and that was first revealed in just about 25 years or 27 years ago. And we're constantly looking at that prediction of continued expansion. And there's some questions are being raised now based on new observations. And we definitely want to understand this business of dark energy and dark matter. It's so dominant in the way the universe is behaving. It's just embarrassing, frankly, that we don't understand what's going on there. And then from all this information we've collected, we then want to know, how do we proceed? Because we know that, for example, in the case of measuring the expansion rate, we have a tension between different measures of the Hubble constant, which is how we characterize the expansion rate. Well, what are we going to do about that? What tools are we going to build? And what observatories are we going to create? And is the rest of this presentation is an attempt to answer those questions. Now, I see something here. I see a little typo. There we go. This the business of making sure that what I present to you is at least been through some level of editorial effort. It's a constant battle because every time I add stuff, I add mistakes to the editing. So this is an individual I want to emphasize, Martin Harwit, who's a refugee in the early 50s from Hungary, came to this country with a passion for astronomy and he's still alive. He's in his early 90s and he's still alive, but he persistently over a long period, roughly 50 years, has been guiding the evolution of the plan for exploration of the universe. He's written a series of books. For a long time, he was a professor of astronomy at Cornell and then left Cornell to become the director of the National Air and Space Museum for a period of time, and was a real scientist, and in the process produced these books that gave astronomers a roadmap for exploration. And the first came out over 50 years ago, and these are not just random attempts to offer a program of research to the community. This is a plan that where each book, and you see they're separated by roughly a decade or two, each book leads to the next book as technology and knowledge of the cosmos progressed. He updated his ideas. Now, he's not, clearly, one person is not the architect of the whole enterprise, but he's a very influential character. Here he is when he was director of the Air and Space Museum. And I was fortunate to work with him on a number of projects. He's here on this paper about different schemes to find planets in other solar systems. There's the author list. I'm there, he's there, and a number of other people. Here's another example, and yet another example where he and I had an opportunity to work together, and his influence was enormous. He's still busy at the age of roughly 90, and this book is probably the most influential. This is 40 years ago. It's a 400-page guide to a plan for exploration. So I borrowed some of his artwork to show some of the history that's been so important in our gathering of information about the cosmos. So here we have a progression over the last 500, roughly 500 years, starting in 1600, of how much better our technology is than the human eye. So we see, like right here, 10 to the 3 means at this point, roughly in the early 1700s, astronomers and physical scientists had an ability to see roughly 1,000 times better than you could just with your naked eye. And you could so this is what we call a logarithmic scale. Up here, we're up to 100 million times better. Of course, in the early days, it was all artisan work, making small telescopes. I'll show you a picture right there. This is a reproduction of Galileo's very small but very influential telescope. It used lenses that he produced. This is a facsimile you can find in Florence, Italy, in the Museum of Science. They've reproduced a lot of Galileo's technology, including this. This I didn't put a scale on here, but the lens piece of this is about 1 inch in diameter. And of course, now we have gigantic telescopes. We'll see some of these depicted later today that are 30 meters in diameter. So Galileo, of course, famously showed the moons of Jupiter with his little telescope, which had enormous consequences for him personally, because he was imprisoned for his belief that there are objects other than Earth out there orbiting the sun. But this is the progression we see. Gradually bigger and bigger telescopes. And now this drawing was made 40 years ago, so needs to be updated, and you will see an updated version here in a second. The other thing that Martin focused on was, what are the technologies that influence our ability to study the cosmos? And he has this very nice curve called discovery rate. That is, how quickly, as a matter of time, what are the times in which the invention of observatories was most rapid? And the 1950 through about 1975 was the biggest bump in our ability to observe the universe, because in that period, we invented electronics, satellites, radio, the ability to signal from a satellite to the ground and make recordings that gave us photographs and scientific information about the cosmos that had not existed before. So you see, from 1600 to roughly 1900 or so, progress occurred. Like that dot right there represents the application of photography to astronomy. Up to this time, from the earliest observatories were, again, the human eye, and then small telescopes. And remember, we talked about Messier in Paris in the 1750s, and so sometime around then, making drawings that from a small telescope he had in Paris, and he drew the rough outlines of hundreds of galaxies. But there needed to eventually be the invention of some recording device other than somebody drawing what they saw through a small telescope. And that dot right there is kind of indicative of the application of photography and you're going to see some examples of that in a few minutes. And then there's additional progression as telescopes got bigger and better because of inventions in other sciences, such as material science allowed the creation of large lenses and eventually very large mirrors. And we're going to talk about why mirrors are almost universally used today for scientific observation of the cosmos. So anyway, this is Martin's drawing of from 40 years ago, speculating about what's going to happen in the total number of phenomena. That's what this scale represents. How many different ways are we looking at the universe? And you see we're in the hundreds now. And the expectation is that's going to taper off. We are somewhat confident that we figured out every way there is to study the universe. I mean, obviously, using light of different wavelengths was important. We now have gravitational wave sensors. We have sensors for energetic particles. Maybe there's something out there we haven't thought of, but we have a lot of experience, particularly in the last 100 years or so, pressing in every scientific direction possible to detect what the universe is sending us. And here's a partial list of the most influential types of measurements that we have been making. And a few, even on this list, which again is 40 years old, everything that we are using today is on this list, including gravitational waves. I think I have it highlighted in a second. But we're looking at stars and planets and novae, which are stellar explosions, comets, moons, rings of, and so forth. You can read this list at your leisure. And not everything here is related to cosmology, which of course is the focus of our class. So I've highlighted the parts of this list that are pertinent to making progress in understanding cosmology, and that includes understanding galactic clusters. What types of galaxies form galactic clusters, which cluster typically has between 100 and maybe 10,000 galaxies? What are is there something special about the galaxies that enter into a cluster arrangement? Or do they evolve differently because they're in a cluster than they might have evolved if they were in isolation? So there's questions about that. We love variable stars because remember we build the ladder that allows us to estimate distances to objects using variable stars and characterizing those variable stars well enough to assign distances to them and use that to calibrate type 1a supernovae and extend the cosmic ladder as far as we can. Cosmic rays are part of that group of things, are particles that come into our upper atmosphere and have been known about for roughly 100 years and continue to be a source of information about what the universe is doing, how these things are created, and so forth. Understanding cosmic expansion, supernova remnants. And so I'll just click on these and you see various things. I highlighted this particular one, the red one, microwave. That's the cosmic microwave background. That understanding of it was in its infancy when Martin drew this piece of artwork 40 years ago. So here he has summarized the types of information that we can expect to gather from the universe, and it's a pretty complete list. Electromagnetic radiation, that's all the forms of light of all wavelengths, cosmic ray particles, looking at visitors that come into view, meteors, meteorites. They don't particularly influence cosmology, but they're important to the general study of astronomy. Neutrinos and other subatomic particles, and then gravitational waves. And the idea of detecting gravitational waves 40 years ago was just a dream. And of course, now we have a mature science evolving, and I'm going to show you some results of that as we go through today's presentation. So this is now we're talking about the period from 1960 to 1980. Just in that period, these are the things that were discovered, objects in space that had never been seen before. And the actual measurement of them, the beginning of studying of these things, like the microwave background, which didn't happen until the accidental discovery in 1967, stellar X-rays and so forth. Speaking of stellar X-rays, I had the good fortune to encounter Riccardo Giacconi, a Nobel Prize winner, when I worked on this project that was built by a consortium of astronomers in Europe. They built their observatory in Chile. And you'll see a little note here that I spent some time having him yell at me in multiple languages when I was working on this project. It was all fine. He was a very volatile genius, particularly in understanding the X-ray astronomy. So even in the last 20 years, we've made lots of progress. We already know that we've had a dramatic improvement in our understanding of the cosmic microwave background, but other things have been progressing as well. For example, 20 years ago, Wendy Friedman, no relation to me, put out a paper talking about what are the challenges we face in astronomy and cosmology that need to be addressed. And the three big ones for her at the time, 20 years ago, were that how much of the universe is matter. And in this case, matter includes dark matter and atomic matter. And the cosmic microwave background gives us the answer. We know that 30% of the universe is matter of some form when we define matter as being some entity that has gravitational influence. And we know that galactic formation is the result of atomic matter interacting gravitationally, but also the mysterious dark matter, which has gravitational influence. We don't know its source, but the amount of matter in the universe got solved by the microwave background and other sources, for example, looking at the dynamics of stars orbiting in galaxies and so forth. But her question about the matter density we think, is solved. She also was wondering about, remember this abbreviation we use, this uppercase Greek lambda, is a abbreviation for dark energy. And 20 years ago, there was a question about the dark energy and the total matter. And the cosmic microwave background tells us the answer to this question, how much of each of these exist. And it does it in a way that avoids a major problem for optical astronomers when they look out into the universe. And the key word is dust. When astronomers try to estimate how much matter exists in a galaxy, for example, they have to contend with the fact that galaxies not only are made up of stars and gas, hydrogen mostly, between the stars, but this dust issue is everywhere and has to be removed in a process that's full of doubt. You never know if you're doing the arithmetic right when you try to get rid of the influence of dust that might reside in galaxies. And like people, every galaxy is unique. And so having a good scheme for removing the influence of dust in a galaxy doesn't tell you how to do it in every galaxy. But the cosmic microwave background solves that problem because it has the fingerprint of the early universe that tells us how much dark energy and how much matter are in the universe. She also was wondering 20 years ago about the age of the oldest stars. And up until the invention of James Webb Space Telescope, progress was slow. And there's I wrote a lot of words here that you can take a look at about different schemes for understanding the age of the oldest stars. We now have a tool, James Webb, looking at the oldest galaxies, and without stars, you don't have a galaxy. So we're making progress here as well. And in addition to the guidance you get from prominent astronomers like Wendy Friedman and Martin Harwood, you need a community effort as well. And for decades, the National Academy of Sciences has been hired by the US government to put together what they call a decadal survey. And this involves engaging a few thousand astronomers, each with a specialty in certain areas of astronomy, to write a guide for the next 10 years. So I'm not sure when the first decadal survey was, perhaps 1980. And so every 10 years, we get a product from the National Academy guiding astronomy and astrophysics. And it's not just NASA who's involved in this. The Department of Energy is interested because they're interested in the subatomic world because of their interest in nuclear physics. So they're a contributor. The Air Force is interested because they're very interested in what is called space weather. Not clouds and rain. They're more interested in what is the sun doing? What kind of energetic particles are flowing out of the sun, or other things that are going on in the environment of Earth. And it's called space weather because it has an influence on the survivability of satellites. And the Air Force, of course, and now the Space Command, is interested in building satellites that are going to do the job and last a long time. So the agencies that fund the National Academy include NASA. The National Science Foundation is also involved because they're the ones that build ground-based telescopes for the United States and collaborate with ground-based telescope developments around the world. So you have those four agencies funding the National Academy to develop a decadal plan. And because of COVID, normally these happen on the 1980, 1990, and so forth. But because of COVID in 2020, the report didn't come out till January of 2022. And it's a semi-technical report. There's no equations. Anybody can read it. It's designed to be read by congressional staffers and non-scientists who are involved in the funding process for emphasis in or finding the right areas of emphasis for future investment. So here you can click on this, you can get a copy of the report that came out in 2022, and it's filled with nice artwork and so forth explaining, this is what the cover looks like, and other activities go on as well. 20 years ago, I was involved in this particular effort to focus on the use of robots and humans to assemble large space structures rather than trying to build a giant telescope on the ground and squeeze it into a rocket, which has lots and lots of problems. The idea in this study that I participated in was to figure out how to launch the pieces and then put them together in space. And you could be much more ambitious doing that because you didn't have to perform a giant version of origami to squeeze a telescope into the existing rockets. And building a giant rocket to launch telescopes, it just doesn't make sense economically. It's just so expensive. And so we made an effort, a group funded by NASA made an effort to define how large space telescopes could be assembled using robots and astronauts. And here's another effort to develop a consensus, which is a challenging thing when you get a bunch of scientists together. You can't get them to all agree, so you have to have everybody get a little slice of the pie. These are 4 reports I worked on. It's a challenging thing to get that agreement how to invest. Now, I'll let you read this. This is more the philosophy of how to lubricate discovery? Should you do exploration, try a lot of different, just send rockets and telescopes of all different kinds out there? This requires a lot of money, and you don't know if you're going to get rewards because you're just trying everything all at once. And the alternative is to come up with key questions and then focus your investment on the key questions. In our case, what this class is interested in is on cosmology. What are the unknowns? And they fall into categories. For example, right now we have a known unknown. Why is the Hubble parameter that we try to measure creating such confusion? And because we can't get multiple measurements to agree, that's a problem. And then we have to admit that there's unknown unknowns, things that we haven't thought of that are problems. And, the next generation of astronomers are going to discover that we were really stupid because we didn't realize that there's that thing we didn't even think about that's impeding all of our progress. So there's a discussion here that you might enjoy reading. And there's always this sort of hand-to-hand battle that goes on. This is me lecturing, talking to the public. I was involved in presenting a presentation to the public. Here's an example. This is all about me, you see, inflating my ego. Here I was quoted in the New York Times about exploration of doing planetary exploration and so forth. So there's this sort of hands-on effort, and NASA guides this as the main scientific space entity in the US, tries to have enough public content to engage the public and keep them interested because we need the funding. And then you have to go for the scientific community. You got to go stand in a booth and try to convince the scientists to buy your product. At this point in my career, I worked for Boeing, but I worked for other companies as well, where we had to go to all the astronomy conferences and try to get the universities and other organizations that plan to do science in space to use our company to build spacecraft and instruments. And here I am with one of the astronauts who was involved in servicing the Hubble, and that's me with Neil Tyson. Now, in this process of trying to convince the public that it's worth investing, you need a genius like Charlie Pellerin. He was, for quite a while, the head of astrophysics at NASA. And he was constantly bombarded by the astronomy community arguing, you're not spending enough money on my topic. And what I mean is there are astronomers focusing on ultraviolet astronomy. There are X-ray astronomers, there are radio astronomers, there's cosmologists, there's theoretical astronomers. All of these people want a share of the pie. And when the Hubble Space Telescope was nearing completion, it's getting ready to be launched in roughly 1989, maybe a little earlier. Reagan was still president, so that would have been 88. The astronomers who were not going to get useful data for their part of the effort, of the astronomical effort, the part that was not going to get help from the Hubble Space Telescope, were bombarding Charlie Pellerin. You need to invest in X-ray astronomy. And so he thought, in the waning days of Reagan administration, how can I get these people off my back? I need to help build them an X-ray observatory. So he called the White House. He had friends all over in Congress and the chief of staff at the White House and so forth. And he managed to get a 15-minute meeting with Reagan, but he didn't need 15 minutes. What he did is he took a piece of paper and put a scale drawing of the Russian X-ray observatory that existed at the time, put it on that piece of paper, and he put another picture of the X-ray observatory that the US had at the time, I'm not sure which one he had, so I just put this little patch there. And he said to Reagan, this is what we want to build to scale. It'll be 6 times bigger than the one the Russians have and much bigger than what we currently have. And within about 35 seconds, Reagan said, fine, go to Congress. We'll make sure you get the money. So he didn't need 15 minutes. He needed roughly 1 minute. And we have an X-ray observatory still functioning as a result of that 1 minute conversation with Reagan. So I'm not going to dwell on this, but here are the astronomical objects that we focus on. This part of the list are the ones that are influential in our progress in cosmology. There are other interesting topics, and astronomers are working on them, but their ability to influence our knowledge of the universe as an entity is less than the ones in this part of the list. And then the planetary sciences and so forth are interesting, but again, not influential. Another way to look at this is to look at the composition of all the light that floats around in the universe that's coming from astronomical sources other than stars. So remember, galaxies are just collections of stars. If we subtract the starlight, means for the most part, the galaxies would be dark. We wouldn't see them. But there's still light in the background that comes from the early universe, astrophysical phenomena that are not part of stars and so forth. And this is a depiction of what are the various things we might be talking about. For example, we see gamma rays from a variety of possible sources. Their sources are not well understood, and it would be desirable to be able to have an image of the gamma ray background, just like we have one. Here's the most prominent one. We do have a camera that measures the microwave background, and you see this is the brightest of all these things. We have just enough gamma ray background to know we'd have to be sensitive at this level to see the gamma ray background. We see the microwave background. There's optical background. There's optical light in the universe not coming from stars. We need to understand where it's coming from. Same with infrared, ultraviolet, X-rays, and so forth. We do see radio waves, and we have been making recent progress in understanding the radio background as opposed to the microwave background. And so this is a topic, expanding our knowledge of the light in the universe that's not coming directly from stars is a topic of interest, and you can find plenty of astronomers who think we need to do a better job in these kinds of detections. And there's more detail. I'm going to skip this. There's just more evidence of the different kinds of light sources that might exist. Now, you've seen this before. This is the so-called Hertzsprung-Russell diagram that shows the trajectory of stars as they age, in terms of temperature and luminosity. And we understand, astronomers have been studying these different kinds of stars and how they migrate through this path. For example, our sun is going to go up as it ages, become a red giant, and eventually just a cloud of debris, gas and dust, that will take 2 billion years to get there. And it'll just be a cloud of stuff waiting to participate in formation of new planets and so forth. We understand this, but we don't understand enough. And so there's generally a focus on trying to do a better job of understanding all the physics that occurs as stars age. Again, our sun is one of those stars. And in the past, this group has talked about active galactic nuclei, that is quasars. fueled by massive black holes. This needs more attention too. Now I'm going to pick up the pace here because I'm looking, we have more topics to address. We also need to do work here on the ground to understand cosmology. This is the building at the University of Colorado, a world leader, including Nobel Prizes, in studying the dynamics that we can study in a laboratory environment, how materials behave in ultra cold environments, for example. And deep space is cold. And then we have the Italians have this neutrino and cosmic ray facility in an area called Gran Sasso. We have here in the US an accelerator facility near Chicago for crashing particles together. This is the big one, is in Geneva. This is CERN. And then in California, we have a different type of accelerator called a linear accelerator, again, for studying subatomic physics, because to understand the universe, we have to understand the smallest pieces of it. Here's a description of the exotic stars that we have to understand better. Neutron stars, which are collapsed stars. A neutron star, the mass of our sun, would be about the size of downtown Denver. And the gravity of such a star is just stupendously large. We also, whoa, we don't need that. White dwarfs are also collapsed stars. Neutron stars can become what are called pulsars, spinning neutron stars. And we have pulsars, the radio beams from pulsars illuminating Earth. It's like searchlights, the best way to think about it, or lighthouse, where you have a beam that sweeps over Earth just because it accidentally is pointed at us, and the universe must be filled with these things. We don't only see the ones that are pointed at us. And some information here about pulsars, and of course black holes, and we're going to talk about black holes more as we progress through today's presentation. So now I'm going to launch a new file focusing on ground telescopes. Having discussed what we're trying to measure, let's talk about what we can do from the ground. And notice this is in the lecture folder. This is designated 5.2. So you can find your way through the lecture notes by looking at this numbering. So here are just some examples of modern ground-based telescopes that are doing the best you can, given that you have to look through the atmosphere. And of course, the atmosphere moves and changes all the time. So we have that disturbance to overcome, and we have technology for doing that.
You didn't change to the new slide set.
Okay, thank you. I always need help, and I thank you for doing that. Well, we could do it this way. You should see, is that better?
Yep, that's better.
Okay, so we're up in the upper left. This is a facility in Chile. This is the one, and if you're on the mountaintop in Chile, and there are 3 examples of that here, you can see the southern hemisphere of the sky. You cannot see the northern hemisphere. We also have telescopes in the northern hemisphere, but turns out Chile has ideal conditions. You're very close to the ocean and very slowly varying altitude here, no sharp peaks. So the wind coming off the ocean is smooth. That's important for having high stability in the atmosphere above the telescopes. Here's a facility with 4 big telescopes and a number of smaller ones. Each of these telescopes has an 8-meter mirror collecting light, and these can look at, in a particular night, depending on the ambition of the astronomers, they can look at 4 different objects, or they can get this whole collection of telescopes to agree and collaborate and look at one object as if they had a telescope the size of this piece of the mountaintop. And we'll talk more about that in a second. So this is a European funded effort in Chile. I had the opportunity to work on this project. We have in the northern hemisphere, the big island of Hawaii is the best place to look at the sky. On the dormant volcano Mauna Kea, here are two matched 10-meter telescopes, paid for by the Keck Foundation, and we'll see more about the Kecks in the next hour or so. And they can collaborate and look at together. They can look at the same object and simulate a telescope the size of both of those. Then we have the Vera Rubin. I'm going to tell you much more about that today. This is in Chile. This is an international effort to make a movie of the evolution of the cosmos. And I'll explain how that's going to happen here in a few minutes. And then the Europeans who built this are not done. They are building this behemoth. This picture was taken, I think, in August of 2024. This will be a telescope not with an 8-meter mirror or a 10-meter mirror, but with a 30-meter mirror. So let's jump into the history of telescopes, again, dating back to the very first ones, Galileo 1600. And you see again, a logarithmic evolution, 1 centimeter, 10 centimeters, that's 100 centimeters. So that's a 1-meter telescope. Those started appearing in the early 1800s, but we're not done because we've invented a new technology. The original, or two new technologies. Up until about this point, all telescopes used refractors. So that means the light passed through a lens like your contact lenses or glasses. After that, people focused on building mirror telescopes. And let's go back here. All of these are mirror-based telescopes. That is, the light encounters a giant mirror and gets guided to a succession of other optical elements, ultimately getting to a camera, which can take pictures. And of course, nowadays we use electronic cameras. But so right about here, there's a transition from lenses to mirrors. That's one big leap. And then the limitations of mirrors became evident around the time the Keck telescopes were built. And so they were built using segmented mirrors. That is, not one gigantic monolithic piece of glass, but multiple computer-guided small pieces. We'll get into this in a second. So here's the history. Now, this is from Wikipedia, and it's out of date. But you'll see, for example, in the old days, the Hale, this was an old style 200-inch telescope. It's still in use as an educational tool, but you can see if you follow through here, the size of telescopes. And the way these pieces of art are drawn is consistent with the kind of technology. So, for example, this is the Russian 6-meter. And because this is filled with color, that means it was made with a single piece of glass. Whereas the Hobby Eberly is made with hexagonal segments controlled by computers to overcome multiple kinds of problems you have when you segment a telescope. And you see segmentation in that gigantic telescope that under construction right now in Chile by the Europeans. Actually, this thing, the EELT, is not going to be built anytime soon. This one, the 30-meter telescope, is in doubt because of an issue I'll introduce. But you see, these are segmented, and every segment has to be managed. Here's a tennis court or a basketball court for reference. By the way, this Russian telescope was a disaster because they built it on a mountaintop that had poor atmospheric conditions above it. They should have known that before they built it, and the result is the telescope is essentially useless. So you have to do a lot of monitoring of the weather to learn about the turbulence in the atmosphere above the telescope before you make the gigantic commitment to build something like this. Here are the Keck telescopes, two 10-meter telescopes with segments. And then to save money, you could build two identical telescopes. That's what the Geminis are. Of course, Gemini refers to twins. So my colleague Jim Oshman was the program manager, and for the Geminis, one is on Mauna Kea in Hawaii and one is in Chile. And they built identical telescopes, so you get the savings of mass production for all the complexity that goes behind these things. So you have either monolithic, that is these kinds of single piece of glass forming the mirror, or segmented mirrors. And even in space, the Hubble Space Telescope, which is somewhere, here it is. These are all to scale, by the way. So there's the Hubble, 2.4 meters. You can have single aperture, a single block of material forming the mirror, or you can do segments, which is the James Webb Telescope depicted here. Computers is what lets you do this segmentation, because you have to manage all these pieces. And something like the 30-meter telescope has a huge number of pieces. So you get the idea. This is more history. We don't have to look at that. So when I keep talking about mirrors, how does this work? So here's an example. Here's starlight coming in from the left, hits a big mirror. And ironically, the mirror has a hole in the middle. But that's necessary, and you'll see why in a second. Light from this annulus goes to a secondary mirror, and that red line there, and the red lines you can barely see there and there, that's all you really need. It's a microscopically thin layer of silver or some other, depending on the wavelength you're operating. It's a metal surface, and the rest of the telescope is there to hold that thin metal in the right shape. So the light hits the primary mirror, hits the secondary mirror, and then goes through the primary mirror to additional instrumentation and cameras. Here's an example. This is the Keck telescope. Each of these segments is about the size of a backyard picnic table, and each one is controlled by computers to deal with what's going on in the telescope as you track an object moving across the sky. The telescope has to move because of Earth's rotation. As the telescope moves, the gravitational loads on the components changes. So the telescope has to detect those changes and remove them with microscopic accuracy. So this is the primary mirror of one of the Keck telescopes. This thing here is the back of the assembly that holds the secondary mirror, and hidden out of sight is the hole that's this hole. Now here's a monolithic 8-meter primary mirror. This is part of what's called the Subaru telescope, and this is a single piece of glass, a special kind of glass that changes very little with temperature change. And then it's coated with, in this case, aluminum, and then additional coating to protect the aluminum from oxidation. And then once a year or so, you have to strip this off, put this in an acid bath. And they have a bath up on the top of the volcano. They have an envelope. You can slide this in, strip the metal off, and recoat it. And they have to do that about once a year. So that telescope, that's the Subaru, and that's this telescope on the summit of the volcano in Hawaii, and all the technology they need to control this telescope is in this cylinder right down here. Here's the Gemini South, an identical design in Chile and Hawaii. And this is the history again, but notice this dashed line. This is the growth path that it's allowed by segmentation. If you pick out the telescopes that appear as dots here and draw a line through the segmented telescopes, you're on a different trajectory in terms of cost and complexity or mass. The Vera Rubin telescope, which just came online in June, is based in Chile, and it's probably the last monolithic mirror telescope that will ever be built. It's very unique design. So they have this big cylinder, 8.4 meters, with a curvature that has the outer annulus is of a single curvature, and then it has an inner annulus of a different curvature because of what they want to do. And I'll describe that after the break. So here are some more depictions of multi-mirror telescopes. This is the Giant Magellan Telescope, 25 meters, and this is in development. And here's a artistic picture of the Vera Rubin that just came online. There's the Milky Way in the background. And way off in the distance, you can see the light of Santiago, Chile, I guess. Or no, maybe, sorry, that's the sunset. So here we have another depiction of one of these giant ground-based telescopes. The primary mirror is here, surrounded by all this structure to hold it in place. The secondary mirror is in this assembly that mirror is facing the primary mirror. And when this thing is running, everything is moving. This assembly is tilting, this table is rotating, again, to follow this astronomical objects. This whole thing is moving, and as it moves, gravitational forces cause this structure to change. So this moves, and the shape of the primary mirror is adjusted so that the image quality remains good, even though the telescope is rotating and tilting. So what the idea is, we take advantage of the fact that the primary mirror is flexible. A way to think about it is, if you think of the magazine, Time Magazine, remember Time Magazine? Pick it up by a corner and it will flop under the influence of gravity. And that's what would happen to these mirrors. If you just picked it up by the corner, it would just sag. So we have to have the technology to control that and remove that sagginess and keep the image pure and distinct. So let's take a break, and I'll tell you about the segmentation management for these are examples and photographs I'll show you from the Keck telescope. So let's take a 5-minute break. It's now 2:02. We'll come back at 2:07. Okay, I'm back. It's 2:07, and let's continue to look at the technology that's required to manage the Keck telescopes. Remember, there are two Kecks on Mauna Kea right next to each other. Each 10 meter, the primary mirror is 10 meters in diameter, and you need this kind of structural support for the material, this hexagon that supports that thin layer of reflective material. And so you need that under computer control, constantly monitoring what's going on. In addition, a relatively new advance is adaptive optics, which takes the disturbed light coming through the atmosphere. Remember, we're focusing on ground-based telescopes right now. The light coming from the atmosphere is constantly changing and distorting. So we have a mirror here that is frequently referred to as a pizza pan. It's under computer control. It has little pistons behind it that change its shape to accommodate the distortion detected by looking at a reference star, a star that is jiggling and is bright, allows you to control the pizza pan to look at a dim object. And so we see some examples here. If we turn the adaptive optics off, we see fuzzy light. It's hard to discern what's going on. Now we turn on the adaptive optics to correct for the atmosphere, and we see there are really three objects here. There's this one and a pair here. And here it is in a three-dimensional depiction. This is not a ghost, because it's Halloween. This is a picture of the bottom of the space shuttle taken from the ground without using adaptive optics. You get all this fuzziness, and here it is using adaptive optics. Here's an example looking at Uranus and Pluto, I guess. No. So this is a great invention. And so originally the idea was to look at bright star that was bright enough to stimulate the signals you need to do the correction. But that's rarely the case, that you have a bright object next to a dim scientific object. So the idea is, well, let's make a synthetic star. And that is done by shooting a laser beam up to the upper atmosphere of Earth. Don't get the idea that we're sending a laser beam to the Milky Way, out to the perimeter of the Milky Way galaxy. That's not what's happening here. We're taking advantage of material that is deposited in the upper atmosphere of Earth by incoming meteorites that burn up and leave metallic mercury, sodium, a variety of materials constantly being fed by incoming dust from the solar system. And you can cause those things to glow, and you can pick where you want them to be by using this laser beam. And in fact, the modern version has multiple laser beams to correct the optics. Now, the idea of using optics to help astronomy also stimulated the idea for me and my student to have a version of this that we would put on a orbiting spacecraft to get a better view of Earth. And so we applied for and got a patent related to the same kind of technology. Here's a telescope looking at Earth, and here's the pizza pan that I mentioned under the control of various kinds of computers, and looking at and doing corrections while the camera is taking pictures of Earth. And this has, in addition, a medical application. This is a drawing I got from a ophthalmological company, where they're intending to have a very high resolution image of the retina of this eye. And here again, there's the pizza pan and computer control, so that even if the patient moves their eye a little bit, or there's defects in their surface, or they need to correct, and they almost certainly have to correct for the defect in the lens of the patient. You can compare this ophthalmological instrument with, this is the patent drawing I just showed you that my student and I had, and it's virtually the same drawing. So this astronomical technique of what is called wavefront control has other applications. Now, you might imagine it matters where you build your telescope. I already mentioned the Russians made a terrible mistake in their effort with a 6-meter telescope. This is the facility in Chile that I worked on. This is the this is called the VLT, the Very Large Telescope. They're the 4 telescopes. The new Vera Rubin telescope is just south of there, again, enjoying the high quality, stable air and dry air that exists at this spot. And you see other telescopes, there's something off in the distance. So you need high and dry if you can find it. And this spot in Chile is the best place in the southern hemisphere. And these telescopes only see the southern sky. And this telescope, you see, is only about 10 miles from the ocean, but it's got all the conditions necessary for high quality imaging. Here's Mauna Kea, Hawaii, viewed from above. This is a satellite photo. There are the Keck telescopes, various others. There's the Gemini, who has a twin in Chile, and so forth. And the summit is 30 kilometers from the ocean. There's the Subaru telescope. Subaru in Japanese refers to this group of bright stars. We call this the Seven Sisters or Pleiades. And you'll recognize this arrangement of stars if you own a Subaru car. There they are depicted on the front. So this is the summit of Mauna Kea. It's a busy area, and it is the subject of protests because of native peoples consider the summit of the mountain to be a sacred place, and they don't want telescopes up there. There's constant arguing about building, there was constant arguing about building a super telescope, a 30-meter telescope there, but this is effort by protesters blocking the road to the summit and so forth. And it's been a 25-year challenge to get everybody to be happy with putting a telescope on the summit. One path to that was the request that was granted to remove older telescopes and make room for the new ones. And as of yesterday, here's a little news briefing you can read if you wish about progress. And progress is really stalled. There will not be a super telescope in the United States in the foreseeable future. Most of the world does not have access to really good spots. Spain does in the Canary Islands, and they have a big telescope, and it will probably host a 30-meter telescope, and studies are underway. Australia, not good. The conditions are not good. Here's the U.S. ideal place is, of course, Mauna Kea, Hawaii. West Texas, a continental United States, has the best we can do is in West Texas. Is not ideal, but it's okay. Chile, of course, has multiple. It's a billion-dollar industry now, and they're building advanced technology telescopes right there on the coast. Canada, they're out of luck. They have no place of significance. South Africa and India all have the same kinds of problems with not having a good site. Now, I already mentioned that here again is the VLT built by the Europeans, that if you build this the right way, you can connect the signals from each telescope can be merged in a big computer complex, and you can simulate a telescope the size of this whole array. That's a technique that's been around for a long time. Oh, and here's a vertical view of the VLT. The U.S. has built versions of this. There's one in Arizona as a demonstrator. And if you, again, if you accumulate the signals you get from all these telescopes, in this case, 4 big ones and a bunch of little ones, you can simulate a telescope the size of this circle. Now, in the radio realm, for a long time, we used dish technology. This is Puerto Rico. Arecibo had a dish type radio telescope, and then it collapsed. Here's one that existed in West Virginia, in Greenbank, West Virginia. It collapsed because these are big, heavy structures. The Chinese have the best of these now. They formed, and there was a geologically desirable site that had kind of a bowl-shaped behavior, and they built a hemisphere, not quite a hemisphere, a geometric shape that's appropriate for a radio telescope. And these things only look upward, like this one. They have a trapeze here that you could move around to view different spots on the sky, but you can't move this thing. It's gigantic. This is the new design in Greenbank to replace the one that collapsed. This one can tilt and move around. So radio people always are striving to do radio astronomy, and they've come up with this scheme where you have dozens or hundreds of small radio telescopes spread out. And then again, as in the case of the VLT I showed you, you can aggregate the signals from all of these and simulate a stupendously large radio telescope. Well, the biggest one we have in the US is in New Mexico, out in the desert, the Very Large Array. In Chile, the most modern one is ALMA. And with these kinds of arrays of telescopes or big tilting telescopes, we can do a great job. And here are the locations of various radio telescopes that can be aggregated to produce an equivalent telescope to one almost the size of the face of Earth. And with that, you can get detailed imagery for nearby objects. This doesn't work for cosmology, but this is the picture. I think this is Mars, or no, probably Venus. I don't. So here, just very quickly, my wife and I had an opportunity to tour the Keck telescopes in 1998. And you see all the technology that goes on because you're managing all these segments. They're all independent, managed by computer action. Here's one of the segments. And without the mirror coating, you can see right through it. This is a specialty kind of glass. If you put aluminum on there, you get this kind of effect. And this gives you a sense of scale, kind of like the size of a backyard picnic table. And the advantage of doing these segments is you can every day, because this telescope is not active during the day, every day you can take out a segment that has the reflector material has degraded, and you can put in a fresh piece. So they don't have to shut down the whole facility to replace the coating. So I talked some time ago about recording images, and in the earliest days of using photography for astronomy, the Harvard Observatory hired women to inspect glass plates. This is how the recordings of the sky were made. They were made on glass plates. Groups of women, they were called computers, studied the locations of various stars the astronomers were interested in, and so forth. And even up to the 1970s, even for our intelligence community, they were still using film. Film is better than glass plates, but the Corona mission was one, you might remember this, where the spacecraft flew around, took pictures of our enemies, and then dropped a canister of film caught by this aircraft, and then they processed the film. Well, finally, in the mid-70s, we started getting electronic detectors. So here's an example of Henry Draper, a pioneer in using photography for astronomy. And he was able to take pictures like this. Nowadays, we can do this. This is Jupiter. Here's 1880, one of his pictures. Here's one of the large glass plates. And these are still around. They are continuing to be processed because they have hidden within them information about the sky as it looked 100 years ago or so. Nowadays, we use this, and we have big mosaics of these photodetectors. They're essentially like what you have in your cell phone camera. And we've gone from this kind of performance from the Corona spacecraft to this kind of performance where you can see a beer can. So the Rubin telescope needs attention. It just came on and it's producing sample photographs to prove that it's working, and it's working beautifully. In June of this year, they had their first light. This is a special telescope with an extremely wide field of view. That means that it's able to cover large areas of the sky very rapidly. In fact, its view of the southern sky will be reproduced every 3 days. And so from that, that's why I say we're going to have a motion picture of the evolution of the universe, because the Rubin telescope has this ginormous field of view illustrated by this bluish square. The James Webb telescope has a field of view of that circle. The Hubble has a field of view of any one of these little squares. And so there's this stupendous amount of data is going to come out of the Rubin telescope. It's a ground-based telescope, so it does have to deal with the adverse influence of the atmosphere, but it's going to take pictures essentially every 3 days of the entire southern sky. Here's a sample photo that was just released in June, and you see it's a high performance. It shows many, many galaxies and so forth, and just the output is going to be a huge amount of data. And here's a little quip for you. The Hubble Space Telescope, to do this image, would have taken 500,000 years because of its tiny pinpoint field of view. And the Rubin is designed to find, let's say they find something interesting here, they can have the Hubble telescope go there and study that spot in detail. And here's that mirror I talked about. It's probably the last big monolithic mirror that will be built for earthbound viewing. So it has one shape in this outer annulus, a different shape in the inner annulus, and the curvature shown here is a extreme exaggeration. And then it does have lenses. I mentioned that we're trying to avoid lenses. Well, because of the huge field of view the Rubin telescope is going to achieve, it needs some glass. The light has to go through glass. But as you see, it's working great, and it's going to be a huge benefit. And here you see a comparison, Hubble, Webb, a wide field camera the Europeans just launched called Euclid. And here's the Vera Rubin with its gigantic field of view. This illustrates the field of view that these various telescopes are going to have. So the expectation is a Rubin is the last one with a non-segmented primary mirror. The 30-meter telescope that the Europeans are building originally was planned to look like this, with hundreds and hundreds of segments. And now let me show you. This is what it will look like when it's done, and it's approaching being done. This is this. And this is a picture from a year ago. And you see all around it is desert, which means low humidity. And because of its location in a terrain that does not have sharp peaks, the wind flow is very smooth and predictable. And so it's going to be the highest performing telescope on Earth. Here it is compared with the pyramids in Egypt. And it has this this is the way the light from the sky comes down, primary mirror, secondary mirror, a tertiary mirror is, oh yeah, this is a third mirror, and then a couple more, and over here you have cameras. So here it is, whoops, here it is, you see, with humans to give a sense of scale. Okay, now I'm going to try to be smart. Let me close this, and then I'm going to remember to share this space-based telescopes. So you should be seeing a whole new screen. Shout if you don't. So space-based telescopes, uh, this is Hubble being serviced by astronauts. We can't do that anymore. The prime location for space-based telescopes is 1,000,000 kilometers away from Earth. Again, here's Hubble being serviced from the shuttle, which doesn't exist anymore. Here's me with John Grunsfeld, an astronaut who worked on all the servicing of Hubble, including correcting the optical defect that was discovered right away when Hubble was first launched. So here's a comparison. Here, this is the Hubble Space Telescope. There's its 2.4 meter mirror. There's James Webb, 6.2 meters across the diameter. And let's make sure that we don't get confused by what appears frequently in the press, that the James Webb replaces the Hubble Space Telescope. That is not true. The Hubble Space Telescope works at shorter wavelengths. There is a little overlap with what James Webb does, but the James Webb is designed to operate at long wavelengths, infrared wavelengths, to see the oldest objects in the universe. And we know they're old because the redshift has shifted their light way out into the infrared long wavelengths that James Webb can see. Hubble cannot see those wavelengths. At the same time, Hubble can see ultraviolet light, short wavelengths, and Webb cannot. So one does not replace the other. So here, again, a comparison of the size of the primary mirrors. And here you see what's the essential parts of any space telescope. You have the primary mirror looking out to this direction. So the stars are out here. Light comes in, this is the back of the primary. There's the secondary, and then the camera assemblies are here. Some of the cameras on Hubble are built in and cannot be replaced. Luckily, some of them were replaceable. And again, here's Grunsfeld working on the replacement that fixed the optical defect in the primary mirror, this piece with the green. But you have to have power. So we have solar panels. We have to have computers for managing the telescope. You also have to have an attitude adjustment technology to point the telescope in different directions. So there's a whole lot of complexity here, far beyond what's involved in the telescope itself. You need communication antennas, and the Hubble now is in its 32nd year of producing scientific information. It came online in early 1993, and it's been aloft for 35 years. And it's probably going to last another 10 years. At some sad point in the next, say, 10 years, they're going to have to throw it away, which means dropping it into the Earth's atmosphere where it will burn up, which is be a sad day because it's the most productive scientific instrument ever built. Here's the James Webb under construction. This is the origami I was talking about. So this is part of the primary mirror with one wing in place and the other wing folded. That's why it's going to be hard to build a bigger version than this of a space-based telescope, because even if you fold this up, you've reached the limit of existing launch vehicles. So here we are 1.5 million kilometers out here at a point of gravity balance called Lagrange point 2. That's where James Webb is now. It's a great place to be because it's away from the heat radiation of Earth, which would tend to want to warm up the telescope. This has to be a cold telescope to see infrared light. No astronomers are going out there. You can't go near it. It went out on this kind of crazy trajectory, orbited around, and it's now sitting at this L2 point, and it'll be there for at least 10 years. Well, that's its expected life, but NASA is really good at building spacecraft and instrumentation that lasts longer than their design life. Let's see, we're going to launch this. Now I have to change. I gifted my husband these pants. Yeah, we don't need this advertisement. So let me share my desktop and you'll see. Yes, I am. I want to show you let's get this out of the way. Skip that. So here's the deployment of the James Webb Space Telescope. I'm going to turn the sound down. I might not go through the whole thing. I want you to see. Yeah, we'll watch the first 3 minutes or so. Now, this video was built before the spacecraft was launched, and it's for engineers like me. It's terrifying because it has so many computers and so many deployments of hardware and thrusting of rockets, and the complexity of this whole process is just fraught with disaster if anything goes wrong. Everything had to work, and it did. The good news is, and you see we're now 10 hours into the flight, they started deploying. I made an initial correction to get to their eventual location. And eventually here we're going to deploy solar. We got one solar panel out, so I got to start making power because up to that point it was running on batteries, and you have to communicate, so you need antennas and another thruster activity to correct the trajectory out to L2. Let's see, I might just jump ahead. Now we have the deployment of the first radiator panel that guarantees that the spacecraft is going to get cold. Remember, we're doing infrared astronomy with this observatory, and it has to be super cold, which means and it has to be protected from sunlight. That's what one function of these mylar sheets. They're about the size of a tennis court, and they are layers. So you have to spread the layers apart, kind of like what you see if you look at the radiator of your car. There's lots of little surfaces. So you unroll the cover, and then, like I said, there's just no end of complex test activity to get all this stuff just right. And you see now we're separating these layers, protecting the telescope and its instruments from the heat from the sun and earth, and giving a path to these radiators so that waste heat from the spacecraft can radiate out through these slats. So we'll jump ahead. This is the way the spacecraft looked prior to deployment of the mirrors. So the secondary mirror, you see it going out on stilts. There's the secondary mirror. The design of this is just like Hubble. It's a primary mirror, secondary mirror, and instrumentation. Then there's radiators opening to get rid of waste heat from the spacecraft. And we're almost ready to do science. We have the wings out. And then they had to wait for the spacecraft to cool down. So let's get rid of that. I learned from bitter experience, we have to stop YouTube or it'll keep playing all sorts of movies that we don't care about. So versions of this, of James Webb, are also being considered, and you see some examples here, like bizarre versions that are mostly telescope with a little bit of spacecraft, like this one. That looks really flimsy, but if you have the right computers doing the right things, that could work. And in this case, you would not have a 6-meter primary mirror. You'd have a 25-meter primary mirror. Oh, and there's the origami that I was talking about, where you fold everything up and then deploy it very, very carefully. You can also take advantage of the schemes I mentioned about ground-based interferometers, where you have separate observatories all flying in formation and sharing their data with a mothership where you build the imagery and the science that you want. So this is something else I worked on, where this is a scheme for detecting planets in other solar systems, multiple separate spacecraft flying in formation with the highest possible precision. Okay, so let's get rid of this. And now we're going to go to part 4 of our presentation. And because I'm sharing, well, let me just check, make sure I'm sharing the whole screen. Yes, so you should be seeing everything just fine. Now we're going to talk about gravitational waves. Oh, sorry, we're going to talk about imaging of black holes. This is a new technology, and it employs the scheme of multiple different observatories merging their data. This is a scheme that, like this, is, remember, this is how radio astronomers work. They have these dishes, and they can aggregate the data. And there, once again, there's VLT. The difference for the Event Horizon Telescope is, instead of having a bunch of telescopes all within sight of one another, here we use the entire Earth. So we have the Greenland telescope. These are all millimeter wave telescopes. These are a form of radio telescope, one of which is the big ALMA complex in Chile. There's, I forget the name of that one. Here's one in Hawaii, West Texas, South Pole, and that's just one side of Earth. Here's the one in Spain, South Pole again. And by linking these together, we can synthesize images as if we use the entire Earth as a receiver. Now, this is a more modern picture, which adds 2 more telescopes. One in Kitt Peak, just very close, these are together, and in France, Noema. So the modern network of millimeter wave telescopes is this. So they're all on a side of Earth that limits where you can look at any one time. Now, as Earth rotates, your view of the sky changes, and this has been exploited to look at black holes. So here, when this idea first came forward, there were candidates for what black holes should we look at. Remember, the black hole is black. You can't, there's nothing to see. But surrounding it is a cloud of gas and dust that's destined to fall into the black hole. We can see that. It's material at enormous temperatures. And here in the center of the galaxy, of our galaxy, Sagittarius A star, abbreviated this way, there's a black hole, 4 million solar mass black hole. That was a candidate for the first experimental imaging with the Event Horizon Telescope using all these millimeter wave telescopes. By the way, these can be simple to create. A bunch of chicken wire, not quite, but a bunch of wire and computers, and you got yourself a radio telescope. The other option was to look at a much more massive black hole in the galaxy M87. And you'll see that we have done both. So prior to the Event Horizon Telescope, various observatories, including the Chandra X-ray telescope, that's the one that Reagan approved after about 1 minute of thought. That space-based telescope has imaged the vicinity of a black hole and this jet that comes out. And Hubble has done pictures of the jet, but nobody had seen the details of the accretion disk. So this is just words saying what I said. The accretion disk was predicted to look like this. Various models of how black holes behave when they're surrounded by a cloud of gas and dust that's in the gravitational grip of the black hole. So this depends on the details you put into your model. And the question was, would we ever see an accretion disk and be able to confirm our model? So this, again, this is an accretion disk. The black hole is inside this event horizon. All the material that's fallen in is trapped inside the event horizon. You get a jet coming out from the magnetic field produced by the flow of this ionized gas and dust. And you see a Doppler effect or a redshift effect, because if you happen to be looking, if the axis of rotation is upward and downward, you would see the gas in the accretion disk approaching you on this side and receding on the other side. So again, you don't know exactly what you're going to get. You've seen this drawing before. I showed it last week. It's another artist's depiction of what goes on near a black hole. And here in 2019 is the result. So this is from, let me move this out of the way. Let's go back. This is the foreground radiation from the accretion disk, and this is from the far side of the black hole, light that has passed over top of the black hole and made its way to our antenna system. So that's what's depicted here. The accretion disk looks like this. You put a black hole right there, and this part here, farthest away from you, still is visible because of the bending created by the presence of the gravity of the black hole. And this part here is this. Now, these images, if you're interested in more detail about this, there's this fascinating book done by Kip Thorne, one of the founders of the movie Interstellar, which is a pretty close to accurate scientific depiction of what happens near a black hole. You might be interested in getting this book. It has wonderful art and an explanation for people like us of what black holes do. Here's a movie. Oh, not quite yet. So what's interesting, this is from the first images they got, and you'll see the black hole, the glow of the accretion disk is not static. You see here, it has this bright area here, and then there's a dim area there just a few days later, and it's even dimmer there. So this might be indicative of how the black hole is eating the neighborhood, that it's consuming the stuff that's available for it to eat. So let's take a look at why we see this kind of behavior. And again, You probably had, oh, we're good. So here we are over here observing the black hole. The black hole is this black object here that illustrates the surface of the horizon of the black hole. And here's light here. This is supposed to depict the gravitational pit created by the black hole. So you see these light rays are bent on their path to us. The ones in the far distance get curved, and some of them end up arriving at the image that we end up seeing, like this. So by 2021, I mean, it takes years to process this data. By 2021, even more sophisticated results came that indicated all these kinds of details. And you can read these as you wish, but the black hole in M87, 6.5 billion solar mass black hole, 54 million light years away. So we're safe. Don't go near there. And there's more information coming from the Event Horizon Telescope. It is not just a way to take a picture. It produces data. Look at the temperatures, the electron temperatures in the accretion disk. So that number right there is 10 billion. And different places in the accretion disk are multiples of 10 hotter than that. So 100 billion degrees. Then they put their genius caps on and they measured something called the polarization of the light coming from M87. These lines indicate how the magnetic field of the black hole, which is almost certainly a spinning black hole, how the magnetic field is interacting with the debris that's about to fall into the hole. And we see these lines indicating magnetic field. And I'm going to skip this. So originally, this is the kind of data we got. Not a lot of detail or no detail about the magnetic fields, but you could see over a period of days this bright area changing. Now we're getting these magnetic fields. And what's more, this picture is of the black hole in our galaxy. So this picture is from the black hole in M87. And this one is the one that's close to us. And notice all the bright area is, if we put a circle on here, the radius of Mercury, that's the closest orbit, closest planet to the sun. All this glowing 10 billion degree plasma is close to the black hole right there. That dot is the center of the black hole, and all this activity is confined right next to the black hole. So there's plenty of data now coming out about Sagittarius A star. That's the black hole in our galaxy, and it's much smaller than the one in M87, but it's a lot closer. So you're able to get these kinds of details. And I'm going to skip this. And even just in the last 2 weeks, there's a new press release from the Event Horizon Telescope, EHT, new results that they have from data collected in April of 2021, and it took years to process. This is an active area of research, imaging of black holes. Now let's finish up. We have about 10 minutes to look at the other big advance we have in looking at the cosmos, and that is gravitational waves. So this was a highly speculative enterprise funded by the National Science Foundation here in the United States. Kip Thorne was one of the prime movers of the effort to build a gravitational wave observatory But when this was underway, money was being spent to develop technology and find the right place to put these observatories. The question remained and was unanswered. Are there gravitational events that we will see if we build this observatory? Without the observatory, you don't know if there are gravitational events. And in almost all cases, the events are mergers of massive objects. Early astronomers were people who were just walking around at night and they could see there are stars. Let's build telescopes to look at those objects. In the case of the gravitational wave observatories, nobody had ever seen a gravitational wave. There's only way to detect it is to build this thing, and it's a challenge getting it built. So here is an aerial photo of the one in Louisiana. It has a partner in the state of Washington. We need two of them at least so we can exclude common events. For example, if there's an earthquake halfway between the two observatories, it would shake both of them. And so we know about the Event Horizon Telescope. Did we ever have any evidence of black holes or gravitational waves, I should say, prior to this? Well, there was speculation. This is a picture of the frequency we get from pulsars, where the two guys who eventually won a Nobel Prize, Hulse and Taylor, managed to find binary pulsars. They are extremely rare, but what happens is it's two supermassive objects orbiting around one another, and the frequency that we see of those lighthouse beams hitting Earth changed over decades. And see here, you see 30 years of observation. If you assume the mass of the pulsars and go consult with Einstein's equations, you get that this object, this binary pulsar, two pulsars in orbit around one another, they should generate weak gravitational waves. We don't see the waves in this case. What we see is the orbital period changing slowly over 30 years. So there was a hint that there are gravitational events that we might exploit if we built the right observatory, but no direct detection of gravitational waves had ever been seen. These are the pulses you get from these pulsars. There was effort in the early 60s. This is Joe Weber, a professor at the University of Maryland, where I was an undergraduate. And I did not take this picture, but I could have, because his door was open and you could see him working with this huge block of or cylinder of aluminum, trying to detect gravitational waves. We now know this scheme doesn't work if you do it at room temperature, but worldwide, researchers are experimenting with low temperature versions of Weber's pioneering detector. But what really works is laser-based observatories, where you share highly precise laser beams and you can see the effect of black holes. Now, this again takes an international effort. Here are the two US observatories. Here's the one in Japan. Here's the one in Italy. Those four are the principal participants now in detecting gravitational waves. And you can look at the details here as you need. Here's the archive of results. So what we have here vertically is the mass of objects that we're dealing with. This information comes from the gravitational wave sensors. The yellow ones here are neutron stars, and in some case, and next to them are neutron stars that have merged to produce black holes. So if you get a orange dot here that merges, these are about the mass of the sun. They produce a low mass blue dot, which is a black hole. And you see blue dots merging to produce another more massive black hole. So the things that are of interest here include neutron stars merging with black holes, eaten by a black hole. The biggest black hole that has resulted from these observations is just over 200 solar masses. We need a different kind of detector, and they are being thought about to get to the mergers of bigger black holes. But right now, the antenna we have, it's called an antenna, can see the merger of this 7 solar mass black hole with this 12. So if you add 7 and 12, you get 20. But in most cases, in all cases, some of the energy of the 2 original objects is radiated away as gravitational energy, bending of space-time that we ultimately detect. So this constantly gets updated. Here's what the signals look like. On that fateful day in 2015, just 10 years ago, they turned on the facilities in Hanford and Washington and Livingston and Louisiana at the same time to do test runs. And they got this signal and this signal. And you overlay these and you get this signal. This shows the predictions that you could get from the merger of 2 black holes. And if you see this, and you tinker with the presumptions you make in your model, you can tease out the mass of the black holes that were involved. The future holds possibilities. So right here is LIGO, and this is the performance in terms of the frequency. You don't have to worry about the details. This is the performance of the Italian and US versions of detectors. Anything below this is not detected. So we see black holes in this little part of this cup. If we build a space-based version, it will be called LISA, and it will see larger mass, massive binaries, that is, merger of bigger black holes. And then there's a scheme using the pulsar systems with super accurate clocks to produce what's called a pulsar timing array, and we might be able to see gravitational waves left over from the Big Bang. Our current systems cannot see that. And there's other ideas. So we're just about out of time. I didn't ask for questions. Or do we have questions? The chat room is empty. The chat box is empty. So gravitational waves, a whole new scheme for studying large massive objects merging in our universe. And fortunately, the effort to build the first observatories was not a dud. It could have been if mergers of black holes were particularly rare, we would have built an observatory and I wouldn't have seen anything. But it turns out the universe is filled. Let's go back. The universe is filled with mergers, and the system's been running for 10 years now. And there are dozens and dozens and dozens of recorded black hole mergers, as well as neutron stars being either merging. Here's an example, a neutron stars merging, maybe producing a black hole. That's why this is partly blue and partly orange. We're not sure what the end product was. So with that, we're out of time. And thanks for participating. Next week, we will finish up and look to the latest news, mostly coming from James Webb and the information that it offers to us. So with that, we're going to bring this. Oh, wait, there's a question. We're doing well, Paul. This is my fall science thing. Mind-blowing. Well, that part, I'm willing to embrace that. And thank you for saying that what I'm showing you is mind-blowing. So I'll see you next week, and have a great week till we meet again.